Ready.
All right. Okay. So let me introduce our speaker today, Leonid Chekhov from Michigan State University and Stiklov Mathematical Institute, and he's going to tell us about symplectic groupoids and cluster algebra description of closed Riemann surfaces. Okay, takes away.
Thank you for this invitation. It's really an honor to give a talk on this nice seminar, and I actually try to make you enjoying. There will be many interesting pictures, as Nikita indicated, and I also have to say that I have to sacrifice a lot of material, and I virtually skip all technical details, and it's all just for be able to come to my main message of today's talk. So I will start with, as you see in the plan, with the introduction. There will be three sources. There will be something that was developed actively in last, I would say, at least 30 years or more. And Anton contributed a lot to this stuff. And we consider the algebras of monodromies of SL. I will actually restrict today to SLN systems, also some possibly some generalizations to other algebras are also possible. And we start with the introduction, considering these monodromies on Riemann surfaces. G will be reserved forever for genus, S will be a number of holes, and N will be something probably less familiar. It will be number of marked points on the boundaries of the holes. So, and then we'll see how we can develop what is called the algebras of geodesic functions. Notably, it's governed by the Goldman bracket. And it is one component of this activity. The other component, also important for me today, will be what we call a groupoid of upper triangular matrices. And this is actually, we'll see how it works. And the first result that I will present will be a solution of this condition of groupoid of upper triangular matrices that I will explain in more details in terms of directed networks and, not surprisingly, cluster variables. Which I think by itself is a neat result, because it was something evading us for at least starting with Bondel's paper of 2000, how to parameterize the corresponding manifolds. But as we'll see, it will produce one more and quite unexpected, I would say, result that we will be able, based on this consideration, based on these results, describe special quivers that correspond to modular spaces of closed Riemann surfaces. Riemann surfaces just sigma G0, so without holes. And at the end, time permitting, we'll speak about perspectives of this activity and so on. So it's all these results that we have here are still unpublished, actually. But we have a paper in preparation with Misha Shapiro, and some previous results are published in our joint paper with Misha, to which I will refer heavily during my talk, and in some of my papers and papers with our Chinese exchange students. So let me start with the introduction. And first of all, I recall well, relatively old and well-established activity related to algebras of monodromies of SLN connections on Riemann surfaces, sigma GSN, and I always here assume that n is not zero. So these are Riemann surfaces when we have mark points on the boundaries. I don't impose the condition that every boundary component must have corresponding mark point, and also some of components may have more than one mark point like this. And we are interested in SLN monodromies, so we just consider monodromies corresponding to passes in this surface, and passes are directed passes, always joining the corresponding mark points on the boundary. So they start and terminate at these points. And these passes, as again well known, are governed by two relations. One is called the Goldman relation. I will sometimes, again, I will use some freedom to swap between semi-classical and quantum version. And we always remember that semi-classical version will be obtained when we take Q to be IH, and we consider just H goes to 0, taking only the first non-trivial terms of this expansion. So Goldman bracket correspond to the case where we have two intersecting passes. Say like yeah. So I don't impose the conditions that pass must. So it can be that it goes to the same point we started with. So there is no restrictions of this sort. And we know that if we have intersection of these passes inside the surface, then this intersection can be resolved using this Goldman bracket. So this Goldman bracket specifically written for SLN connection. And second condition that I will impose, which we call as a pass groupoid condition. So I must again apologize because there are two groupoids. There will be two groupoids here. There will be groupoids of passes in Riemann surface, and there will be another groupoid that is referred to these upper triangular matrices, and they are more or less completely different. So what does groupoid of passes condition mean is that we can compose passes like here, like in this picture. So we goes first from pass from one. So here these mark points are indicated by these numbers, and again I have to remove completely specific. So it happens that if we have a triangle decomposition of the surface, so in SL2 case, it's actual real ideal triangle decomposition. In higher dimension case, it's more topological. We usually don't have a geometrical picture corresponding to it, but we just say that we have a triangle decomposition of all these surfaces such that vertices of triangles actually they are also at the mark points, and to each mark point we put into the corresponding some area between these two mark points. Like for instance, in this picture, this area will be between two mark points in this case, and it will be just this whole boundary component in the second case. And well, somewhere we might have, so if we have more than one mark point, then I just declare this another interval, just the third area or third interval between these 2 points, and we just basically somehow, again, I promise that I will not make into details, and I not always keep my promises. So actually we just identify the corresponding area right to, well, it's oriented case, so we have a notion of right and left. So let's take this area just to the right from the corresponding point and just paint it red. And then the corresponding monodromy will be given by elementary monodromy transformations inside each of these triangles. So, and as we'll see in my talk, actually, the structures inside this triangle are rich enough.
Excuse me.
Yes.
I'm sorry, I'm a little confused. So when you're talking about the area, we're supposed to be thinking of the area inside the hole here, like where is
No. It's on the boundary. It's like I possibly try to draw here. So we somehow associate, because when we do a ideal triangle decomposition, these are edges. These are outer edges of triangles. All other edges are inner except exactly these edges. So let me leave apart a story what happened when we have boundary components without mark points. It can be done. So so basically the only condition that we need just one mark points to define what is a corresponding first homotopy group on the surface based on this point. But if we have more than one point, then we might compose the passes that comes from one point to another. And this composition, to be consistent, must satisfy this groupoid condition that we have here. So if we have two passes, and you see that this composition of these passes in the right is equivalent homotopically to the pass in the left, or vice versa, composition in the left and pass in the right. And you see from this consideration that if we split these monodromies into some elementary transformations between edges of these triangles that we denote as M1 and M2, which one is which? So this will be M2 actually, and this, for instance, will be M1, and we'll see examples in what follows. Then these elementary transformations and elementary transport matrices must satisfy what we call the groupoid condition. And from this picture, you see that to satisfy this condition, we just need to consider only this composition inside one single triangle. So, so in order for all this to be consistent,
Leonid, can I just also ask for a clarification? So you said for SL2, this, you have this ideal triangulation, which is, you said geometric, but for SLN, you just said topological. What do you mean exactly?
It's topological means that we technically consider the same splitting, and well, again, so if I come back to the story, it's Fogg-Goncharov coordinates. So that's we have in all these mark points on the boundaries, we have flags, complete flags.
Okay.
And then topologically, yes, inside each triangle, we consider algebraic structures related to three flags at the vertices.
Okay.
But again, my goal today is to show that it's all can be done explicitly in combinatorial way. All this. So basically, to ensure the consistency of algebras of monodromies, we basically need just two conditions. So we should know what happened with the corresponding transport matrices when we change, when we make a flip in the triangle. So here is an example of this flip, and Gus and Sasha Shapiro, they actually demonstrated not so long ago. You see, it's somewhere about 2018 or in 19 that the corresponding passes are preserved by the corresponding flips for any n. And second, we have this, what we call with Misha Shapiro groupoid condition, namely that if we compose two monodromies, one, you see, it's say M1 here, and this is similar monodromy M1 bar, then their composition gives this third monodromy M2. Actually, it's actually happened to be also not quite trivial condition, as we'll see. But well, again, I have to skip many technical details, and we can prove it for any triangle in Fogg-Goncharov case, and for any n, and even we know the quantum version of this condition, of this groupoid condition, path groupoid condition. Again, I have to always separate between two notions. And here is an example. Here is an example of this triangle. So what are combinatorial objects that we associate inside this triangle? How we can construct these elementary matrices that will play a prominent role in my talk today. So first of all, we have this quiver, which is indicated by blue arrows. So vertices of this quiver are variables, cluster variables, and edges in this quiver, they encode commutation or Poisson relations between these variables. So for instance, if it's a solid arrow, then we have Poisson relation or correspondingly quantum relation of this form. Also, for instance, Poisson relation in this case would be just, and all these relations are homogeneous. So all variables are, so to speak, log-canonical. And if we have a dashed arrow, then we have just half of this relation. Then we have a dual network, which indicated by double arrows here. And for each source and sink in this picture, we may construct in a natural way a path from source to a sink. So for instance, it's not unique, usually, commonly. For instance, here we have one path. And to each such path, again, because we are in an oriented situation, we know what is to the right and what is to the left. We set them to the corresponding, the product of all variables that lie, say, by convention to the right of this path. If we consider quantum case, then we have to also take care of ordering of them. So inside each triangle, the ordering will always assume to be a while ordering. So we can actually interchange variables inside this ordering at our will. So you see that to each path we just set into the corresponding some monomial of these cluster variables. And what will be an element of the transport matrix? So here is probably some explanation how we can construct any such network out of elementary pieces. I will probably skip it for sake of integrity. So because the most important is that transport matrix element will be just given by the sum over all passes. Sum over all passes of these monomials. So it's always some polynomial. If you don't have self-intersections, that it's polynomial with positive integer coefficients. And well, it's very general. It can be defined even, it can be defined for cyclic networks or for acyclic networks. The only condition that we have to impose is that the network itself is a planar. And then in this case, we have this nice algebra, even quantum algebra of these elements that I present here. And if you want to see more details, just have a look at our paper with Misha of 2020. And semi-classical version of this algebra of passes was presented quite a while ago by 2 Mishas and 1 Alec. Okay, so this, well, this actually convinces us that, yes.
Sorry,
questions?
Leonid, I'm a little bit confused about the picture. So like some in the first equation, the right-hand side is non-trivial, but we don't know what's the configuration on the left-hand side. And then the next equation, the right-hand side supposed to be 0, but we don't know again what's the kind of configuration.
Well, okay, Anton. So let me just explain it. So first of all, these algebras, they are probably counterintuitive to those who are familiar with golden brackets. Right, because
that's fine. Just
no, it's indeed. I was confused when I saw it first. Because you see, what does it mean? It means that we have a planar network where we have sources and things. And in principle, we usually impose a condition that they are separated, but in principle, we can also allow some sources interlaced with things in the most general case. And then we can define in the same way as I described. So we can define these elements of transport matrices if we fixed, for instance, alpha source and which one I want, a sink, and I consider just all passes that satisfy these conditions that correspond to this passing.
Okay, now I think I see it better. But for instance, the first picture, which is non-trivial, those they should be separated. But how far something can come in between or not at all?
No, it can be anything in between. No, it's the only condition is they coincide or not. That's it.
Okay, thank you.
Everything is possible. Yes. So it can be arbitrary number of sinks or sources. It doesn't matter actually. So it's very robust, these algebras. And as I say, so they are somehow slightly misleading because, for instance, in this case, we probably would expect that they would commute, but they don't. Their commutation relation is actually proportional to this right-hand side. And these intersecting passes, they commute. So that's what authors, it was also in Fomin and Zelevinsky, I think, paper first. They called it a kissing condition, right? So anyway, what will happen if we use these algebras? Consider a situation when we do have separate sources and sinks. So, for instance, here I have. Let's put it. So sources are on this side, and I have two sets of sinks. One sink set is here. Another, let me probably use different even color, is there. And again, it doesn't matter sizes of these matrices. So there can be, it just occasionally happens that they have the same number. No, it's not necessarily true. They can have different sizes. So these matrices that we make can be actually not necessarily square matrices. And again, it happened. Possibly also it's might be quite familiar to Anton, that if we have this structure of sources and sinks, and again irrespectively of what is inside, we can encode the relations on the previous slide in R matrix form. So for each of these transport matrices, I also multiplied by this anti-diagonal matrix SQ. It's correspond to changing the basis, swapping the basis in the corresponding flag. Actually, so it was also in whole bunch of papers. So first of all, we have this standard Poisson R matrix relation for the matrix itself. And second, if we consider exactly this situation that I described here, so we have part of things are separated from other parts. Then we have this R matrix relation with one R matrix for the corresponding two matrices, M1 and M2. Again, this is very robust. So I don't impose the condition that we don't have other things or sources. No, so it can be interlaced with anything. So again, it is valid for any set of sources and sinks that are or subset of those that are distributed this way on the surface, on the planar network. And yes, and the R matrix is a standard quantum R matrix, what is called trigonometric R matrix. So it's half of permutation. What's more, what we observed with Misha in our paper, that thus defined matrices, even in quantum case, they satisfy also this path groupoid condition. Which means that, for instance, in this case, if I go from one side of the triangle to the other side, it's the same as to going just, if I go from the side 1 to side 2, and then from side 2 to side 3, is the same as going just from 1 to 3. To convince you that it's some non-trivial observation, let's make, well, but before, so first of all, if we have these quantum relations between these transport matrices in each triangle, and one more thing that variables in two separated triangles, they just commute. So all non-trivial commutation relations are inside a single triangle. Then we observe that, for instance, if I consider the composition of passes like here, this blue and red, then now these passes do not intersect. So these passes correspond to SLN monodromies. Not surprisingly, they Poisson or quantum commute because they are separated now in normal sense. If we have this intersection, again, we just indicated so by the corresponding product of transport matrices inside these passes, then this intersection can be resolved in a Goldman way for SLN, where P is a normal permutation matrix. And again, to convince you that these relations is somehow non-trivial, I just make some two examples. So if all these variables z are equal 1, so completely classical case, then the corresponding transport matrices multiplied by this anti-diagonal are of this form. For you can spot a pattern. They're just binomial coefficients here. They're just composed out of binomial coefficients. And interesting property of all these matrices for all n is that the third power of each such matrix is equal to the unit matrix, which in particular implies that basically the groupoid condition is written this form. So application twice of this passing correspond to just one passing of another sort. And well, that's something that again you can check, or you can give your students in linear algebra class to check on the test. So now we change the topic. At the first glance, we change the topic completely. And we refrain from geometry of any sort so far and consider completely different problem, purely algebraic problem. So
can I ask a quick question before you move on? So where you were showing the theorem, you said that these three matrices, M1, M2, they don't even in principle have to be square matrices. So in that situation, that kind of situation would never arise from monodromy, like local systems when you're studying local systems.
No, no. In monodromies, of course, they are all square matrices. Yes.
Okay.
But well, basically, not necessarily. For instance, even there, we can unify this M1 and M2 in one block matrix.
Ah, I see.
And for this block matrix, we still have this condition. So just our matrices will be of different size on the right and left hand sides.
I see. That would be almost like some kind of decomposition of your local system, and then on sublocal systems you have some sort of relations.
That's actually how we can derive this upper relation from this lower one.
I see.
One of these. Yes.
Okay, I see. Thank you.
So consider the following problem. Again, consider a manifold that is given by pairs of matrices. B is just any matrix in GL, and A is a matrix that is unipotent upper triangular matrix. And we just consider such admissible pairs such that the pair is admissible if this action, it's an action in the sense of forms, not in the sense of operators. So it's not adjoint, but it's how so we associate with A components of some form, and when we change the basis, these components are transformed in this way. So the condition is that transformed matrix has the same upper triangular form. Well, it is a famous algebraic object. So some people basically we refer to Karashev and Weinstein and many more, like Kirill Mackenzie was spending decades studying this sort of systems. And we have relations, we have maps like source and target maps. So source maps, of course, they map to the original A, and target map to the obtained matrix A that we also often denote A twiddle. And well, it was known that we have and we have the composition of these transformations, this multiplication morphism, and it was known that we also have a Poisson structures, and we have so if we have these triples, then we can define the projections to the corresponding parts of this triple. So this is projection, I think, P2 source. Yes, so this is P2 and this is P1. And it happens that these projections commute. So this is a very strong condition because it allows to define a symplectic structure on these pairs BA, and even more, the consistency condition of this symplectic structure is the splitting condition. Again, this is a strong condition. So it implies in particular that source and target maps Poisson commute. So this means that basically for any relevant Poisson structure, we must ensure the condition that these two matrices commute. And again, I have to skip many details. It's very nice story, but actually quite an old one. So finally, it's probably culminated in year 2000 when Alexei Bondel obtained a Poisson structure on this set elements of A using this algebraic construction. So people probably never even dreamed about describing the full manifold of these solutions. So they mostly considered some local structures in tangent spaces like algebroids. But even this was very useful because he was able to produce, so to collapse, to leave this Poisson structure to the set of matrices, matrix elements of A. And these Poisson structures turn out to be something very much familiar to people in geometry and physics, because these structures are exactly correspondent to the algebras of geodesics on Riemann surfaces, sigma GS. So is Riemann surfaces with holes but without punctures, such that genus of this surface is was integer part of n-1/2, and s was 1 or 2 depending on the parity of the corresponding n. Yeah. And so it was studied. It was studied before this algebraic structure by many people. So from the physical side by Jeanette Nelson and Tullio Regge, from more mathematical by Gavrilik, Lemik, from the point of relation to monodromies of Fuchsian systems by Borja Dubrovin, Monica Ugalia, and partially Alexei Bondel. And with Marta Mazoka, we had also quite a while ago a quantum version of these matrices. What is unify all that is that these matrices satisfy, so we can encode these commutation relations in quantum case into the reflection equation. Again, this reflection equation is very famous. So it's just on the cover of Alexander Molev's book about representations of twisted Yangians. And so in geometry, this equation holds if we identify the entries with a special finite subset of geodesic functions. We actually presented this subset with Volodymyr in one of our papers, but I don't want to recall that because I want to move further. What was, however, a problem is that when we want to restrict to geometry, we have to consider a Poisson leaves of lower dimension. So we need Hamiltonian reduction to be performed. We know that there was a classification of these Poisson leaves again in Bondel's paper. So it's all consistent with the general construction of this groupoid, but nevertheless, the first problem that we had in old days was actually construction of the corresponding representation in terms of the corresponding coordinatization of just this reflection equation terms. And second problem was also we had some scaling relations that in geometrical case correspond to twists along the corresponding geodesics. And these scaling relations were encoded also in the action inside this groupoid, as you see, so it can be imitated or produced by the transformations, now discrete transformations with some special matrices B. And the first problem that was standing for 20 years, I would say, it was to find a cluster variable realization of a general symplectic leaf, not just a geometric symplectic leaf, for which we had this realization in terms of shear coordinates. And find the cluster mutation realization of these braid group transformations.
Leonid?
Yes.
Sorry. So what is beta and B? So B is a matrix and beta
B
is an
just
operation?
a matrix, and B and beta is a transformation itself.
Okay. Okay. Thank
So
you.
beta is a morphism. So it's a Poisson morphism. It's all these morphisms are Poisson or quantum. So beta is, you see, is a right here. So this is some elementary morphism, and we just make a braid group out of this morphism, and they satisfy many standard relations of the braid group, which I of course drop from this talk. So we solved this problem with Misha in this paper of 2020, and not surprisingly, we just need again just one single triangle from Fogh-Goncharov to encode it. For instance, again, if we consider the same transport matrices that we used before, M1 and M2, and we just take this product of these two matrices, as it's written. It also works in quantum case. In quantum case, natural ordering is also quantum ordering. So then this matrix A enjoy Poisson or quantum, whatever you want, reflection equation. So indeed, to parameterize just general Poisson leaves of this structure, we need just one Fogg-Goncharov triangle. And therefore, we had the Darboux coordinates for a general leaf, and all thus constructed geodesic functions that we associate with elements of this matrix are Laurent polynomials. Laurent polynomials of actually it's maybe it's better to be written in these terms. It's that alpha actually plus minus 1/2. I have to again skip many details why we change from integer powers to half powers, but well, that's happens. That happens technically when we took into account some Casimirs, when we include Casimirs into play. And but you see, so the result of this action is such that, for instance, we obtain some new quivers because of transposition. Transposition correspond to this gluing of boundaries in non-oriented way. So if we had a planar network with planar relations before, after we impose this condition, it's no more planar. But it's actually nice, and it will be important in the main part of my talk, to which I about to start now. Don't worry, it's not very long.
Can I ask a quick question about this theorem that you previously stated, this M1 transpose M2? So previously,
actually, this works for any network. It's not only for this triangular network. It's actually valid indeed for any planar network. So it's again there are very many variations of this relation.
I'm just very interested about this transpose.
That's
so like
you have yes, it's actually a very interesting operation, as we'll see immediately.
Can you think of this kind of the fact that, you know, in order to get this reflection equation, you sort of need to combine your system with the transpose of the system somehow. Is that sort of a general feature that
we'll see? Yes, that it's much more general than we might expect from this exam. This will be in my main part.
Okay, very cool.
And again, so this relation here, it's actually, again, so it can be satisfied in plenty of networks. Basically, we take any planar network on our choice. We just consider these matrices for some subsets of sources and things, and we automatically get the reflection equation. But the next part will be much more specific and will be based on I wanted to spend some time describing the mutations, but possibly we'll skip it. If some people will want, I will have time after. Because again, I'm not quite familiar about the background, but maybe I will just say what mutations are. Because I use it. So in this quiver, imagine that we want to mutate, so variable. So we have a variable, let's call it Z1, Z2, and Z3, and we want to mutate at Z1. Basically, this corresponds to the following structure. So we transform these variables in this way. So we just, instead of Z1, we take just inverse of it. For Z2 that has an arrow towards Z1, we have Z2 is multiplied by this, and Z3 is multiplied on the contrary. So it's actually divided. So these transformations are in general rational transformations on the set of coordinates. And how, but their Poisson morphisms in the sense that first I have to invert of arrows towards Z1, and second I have to add arrow that correspond to the path that go from Z2. So let me probably go this way. So it first come to Z1 and then it goes out. So we have to add one more arrow in. We have to add one more arrow to this picture, but this is just this graph, subgraph, just encodes the new commutation relations between the corresponding variables. So message is that these transformations are not polynomial. And especially because we also have an inverse powers, negative powers of that. Basically, they are virtually, in all occasions, they're rational. Okay, so now consider the following picture. Consider now gluing of two Fogg-Goncharov triangles. And actually, it was on the table for a long. It was actually proposed in Fomin-Zelevinsky paper of 98, 2 years before clusters, to parameterize just matrices, matrices satisfying Lie Poisson relations. So, for instance, for a B, we just have to go from this side to that side. So B will be the product of two elementary transport matrices, M2 and M1. One is upper triangular, another is lower triangular, so B is full dimensional. But what happened? So let's consider this. I just redraw the same picture, and now I have this set of six transport matrices. So we can actually transport from any side of triangle to any other side. And what happens? This is a theorem. Again, I skip all details, just formulate. If we just associate, so we take this matrix B to be original matrix. We know that this matrix satisfy actually Lie Poisson relations of semi-classical or quantum type Dunn matrix. So it's the quantum version is also exists. Then if you take just this product of three matrices, like here, and we use the path groupoid condition in our calculations, we obtain that this product BAB transpose will be an upper triangular. So basically, we actually solve the corresponding groupoid condition completely, because we can parameterize solutions in terms of these cluster variables in these glued triangles, in this quadrangle. Not sure.
Lenya, what are these brackets?
Brackets, which brackets?
The square brackets in the second line.
That just indicates that sometimes you see that in quantum, it's transposed. So it's not always that transposition and inversion commute, especially in quantum case. So this means that basically there is no meaning. It just indicates the order of operations. If it's just one operation, so basically we can remove these brackets. So there is no technical meaning of them.
Okay, thank you.
Just aesthetical, no. So by itself, it was quite unexpected result. I got it just less than a year ago. Just realized that it works this way. Again, if I make two examples, so if we set all this that I equal 1, then for instance, numbers in this, so disregards the signs, they are just, they have a regular structure, you see, it's because of its S matrices, so it's sign distribution is regular and not much relevant to what I'm about to formulate at the last, I don't know, 3-4 minutes. So just to convince you that it works. So if we make this, so again, numbers indicate a number of terms in the corresponding polynomial expressions. And these numbers, even in this example, you see that these numbers are quite large. And it becomes unbearably large for hand calculations by hand very soon. So it's actually we have to resort to some computer simulations. But you see that indeed, if we take these matrices and multiply them, then we miraculously obtain again the upper triangular matrix. And it was proven actually that the Lie-Poisson algebra of B can be, because knowing B, we can construct actually, we can solve the equations that A with respect to A. So it's just a system of linear equations, and we can solve it and prove it that the thus constructed matrices A and A twiddle satisfy the closed Poisson algebra that I drew that I presented here, and simultaneously we can derive this algebra from this explicit expression, because we know commutation relations or Poisson relations between the corresponding constituents. So indeed, it's also satisfy these relations, and in particular, you see that the matrices A satisfy reflection equation, and this map from A to A twiddle is actually anti-Poisson map. So it just the corresponding relations has different sign for A twiddle. And not surprisingly, yes, they commute. Also, the variables inside each of these matrices, they are not commuting. They are the same, more or less the same variables, but their combinations combine in such a nice way that they do commute. Geometry. And this is the main part. That's probably my main message. Again, I skip many technical details. First of all, you see that we again have a gluing, because we have again a transposition. So this upper boundary is glued to lower boundary in this inverse way. So for instance, you see this one glues to 1 prime, and what we obtain, second, we have these frozen variables on the boundaries. But because of this gluing, it also helps to eliminate all these frozen variables, because we have exactly 2n new Casimirs which we just use to eliminate them completely. So now we have quivers without frozen variables. All variables are now mutable, how we call it. And I will consider just one example, namely this one, this n equals 3. So because remember that this 1 and 2, so they are identified. So we actually have just 6 variables in play. And if we mutate, we can mutate it easily. So you'll see that it just what is called in the cluster variable domain, some special cluster that not of geometrical type, but of finite mutation type, X6, and there was no identification of variables for this cluster so far. Now, how it's all related to geometry? Recall that variables of each of these A and A twiddle, they commute. So they now we identify them with geodesics, but geodesics on 2 halves of a Riemann surface. What separates them is called the Markov element. Markov element, which is the same, which is actually preserved by this transition between A and A twiddle. And before, well, basically we didn't have any way how we can go through this boundary that separates these two. So this is for this case, this is the graph for n equals 3, this is for n equals 4. So in general, we expect that on the this left side, we have a closed Riemann surface of genus 2. And here on the right, we have a closed Riemann surface of genus 3. And we just need to find one missing link, namely expression for the geodesic that join these 2 halves. And it was actually some sort of luck that we were able to find it, because it just was, we were just playing with formulas. This is a standard expression for this Markov element, and this Markov element is a central element of the corresponding algebras of A and A twiddle. And it happens that it's also invariant, or covariant, better to say, under all mutations in X6 quiver. So we cannot change it effectively using mutations. And it's long, that you see expression. But it happens that another form of writing the very same expression, if we resort to these quiver variables, cluster variables, is this one, where we just met some interesting expression, which we denote to be GB. Why? We know from Fenchel, Nielsen, Korner that we, and from papers by Nekrasov, Shatasvili, Rosler, and myself, that we can express a twist that is dual to the corresponding geodesic, that corresponding again to this Markov element, just using some explicit formulas, where we have this GB as a part of these expressions. And we just need to check that for any relevant choice of this GB, this relation must be satisfied. And just it does. Again, I skip everything. So this means that we can indeed identify this expression with the missed geodesic.
So what is F in that expression?
What is F? F is some cluster variable. So F is F is here. F is one.
I see.
One cluster variable that enter explicitly, not in some combinations. You'll see immediately that it makes sense. So So we observe, yes, that we have this twist, and we have some strange transformation that correspond to the twist along this new geodesic GB. It's not inside the standard set of cluster mutations for X6, but it happens that it is a cluster mutation for an extent quiver. If we just literally add by hands a new vertex G, and instead of considering X6, we consider what we call in the corresponding cluster classification X7, then all blocks come to their places. And then we have this theorem. It pertains to the smooth Riemann surfaces of genus 2. And for this, we say that the corresponding Teichmuller spaces are parameterized in terms of variables of this X7 quiver in such a way that first, all geodesic functions are elements of an upper cluster algebra. And so they are polynomials in all clusters. So the polynomial form is preserved by all mutations. And these geodesic functions, all geodesic functions, they are generated by Skene and Poisson relations by 5 elements, for which we have explicit UC formulas here. And all den twists in this picture are given by mutations that preserve this quiver. And they are all Poisson morphisms, and they are all just rational transformations. So we have a rational transformation realization of the full modular algebra, modular transformations for genus 2 surfaces. And I am over time, so this will be probably my last statement. But just coming to this picture, you see that these 5 geodesics, so disregard this separating geodesic M. So these 5 geodesic here, they actually enough to describe all structures on genus 2 surfaces. And just to make small remark at the end, what happened in higher genus surface? What happened if we, for instance, this is for an equal 4. Many things are preserved. For instance, the corresponding quiver that we have can be always presented in this interesting way, in this interesting form, when we have these square quivers with sizes, so it's n-1 times n. And to describe all mutations, we still have to add just exactly one more vertex, in such a way that all other vertices of this quiver except this one, they are exactly 4 valent vertices. Then we can say that it's not exactly true that all geodesic functions will be Laurent polynomials. No, because in this case, let me scroll up again. I will scroll up and down. So we here have some sort of Z2 symmetry. So if we have for all geodesic functions in that we consider, they are Z2 symmetric. So we can rotate this pattern by 180 degrees, and they come to themselves. For instance, these 2 geodesics, they are not symmetric, and it happened that they are not expressed as Laurent polynomials, but their symmetric combinations they are. And again, we have a subgroup of whole mapping class group quotient by these Z2 conditions, and this quotient group is generated by the mutation, so they satisfy this rationality condition. But it's still work in progress, so there are still things that we don't know. So for G equal to, for genus 2 is just a theorem. One last remark, I don't have time for perspectives, so because they're bright, but I don't have time to describe them. One last remark that probably genus 2 is so special because it still have it actually has this Z2 symmetry encoded because it's uniformized by hypergeometric surfaces. And how this uniformization reveal itself in this purely real geometric case, I don't know. Okay, so let me stop here. Thank you for your attention.
Thank you, Leonid. Does anyone have any questions for Leonid? You can, yeah. Anton, go ahead.
Yeah. I have a perhaps somewhat naive question, or maybe provocative question. How is it towards the end, the description of the results got a bit complicated? Is it already like the ideal form of the results, or is it the optimal form, or what would, if not, what would be the ideal one? Because in the end you were saying, oh, but maybe lengths of some geodesics are not actually cluster variables, and you need to do this. Okay, yeah, maybe I misunderstood.
They are. So basically we can, if we know these expressions, for instance, so for each geodesic, we have to just to take its mirror geodesic. And then we have a rational expressions for the symmetric functions. So basically we can derive the expression for each geodesic, it will just not be rational, right? That's true.
Okay, you're just saying that the lengths of geodesics, these are not good parameters.
Lengths of geodesics are not good parameters at all. Even it's what known. Okay. So basically, algebraic objects were hyperbolic cosines of lengths always.
Okay, and but you're saying that even them, they're not good parameters, or what? No, sorry, I said the question was
quite good. No, usually they're quite good. So, for instance, again, for genus 2, we have just a full description. So they're all geodesic functions. They are just rational, not rational. Sorry, they're just polynomial, positive Laurent polynomials.
Anton, I'm sorry for interrupted. It seems that we have folding of Teichmuller space over some kind of by the action of finite group, and we describe the quotient. We don't describe the Teichmuller space, but we describe the quotient. And it is accorded on the quotient, not on the original Teichmuller space.
But then, is there some good reason this quotient may be better than the Teichmuller space itself? Whatever, like
what people used to say when even in old days when they considered the braid group action on just this set of unipotent matrices, they used to brag that it is just describe the full modular group. Even in this case, it's not true. Even in this old case, it's still not the full modular group. It's still this quotient by Z2 action. because let me scroll up a little bit. In this geometrical picture, it's also that's something that we described for that we discussed with some topologists. What is which generators here in this picture? So let's consider picture on the right. On the left, we have a full description. On the right, actually, the full modular group we obtain if we say remove one of these, just remove remove this one, this twist around this, and add one twist around one of these. So the number of generators will remain the same. So technically, so to speak, the volume of the group is the same. But this breaks, so adding this new twist breaks this Z2 symmetry, discrete symmetry. So in our case, basically, because the corresponding expression for a single geodesic here, M1, is not rational, it contains some square roots. We still don't know how to, can we actually describe the corresponding transformation. But still it's good enough because it's all, well, how to put it, it's almost the full modular group, except
no, don't take me wrong. I think it's very beautiful. I'm just trying to understand a bit better what's going on, right? So
well,
yeah, no,
I will say for myself, but probably also for Misha, that we probably also we don't know everything. Yes, many things are still in progress here.
Okay. Any other? Does anyone else have any questions? Maybe I have a question. Can you explain again the significance of adding this extra vertex in the quiver,
okay.
and if that can be seen somehow directly in the geometry of the surface, or yeah,
well,
what's the
one thing that we still don't have a clue how we can associate it with the geometry of the surface. So, for instance, these quivers, they don't have a form of geometrical quiver, so they don't based on angulations.
Mhm.
It's just that we use this, our knowledge that how we can identify the elements of the corresponding upper triangular matrices with geodesics in some previous cases. Why it's significant to add this vertex? Well, in principle, you see, in general, we didn't add so much because we still have the condition, I probably skip this, that we impose a condition that some combination of these elements, E square, what AB, what is the rest, A, B, C, D, F, G, is equal 1 to make this transformation that you see on this upper part of the screen.
Mm-hmm.
So technically, we didn't increase the dimension. We didn't spoil the Poisson structure because if we have 7 variables, we now have a Casimir. So before it was full Poisson dimensional, it still have the same Poisson dimension here. But it's convenient because after adding this vertex, we can actually make these transformations again a cluster transformations. So it's I don't know, Misha maybe disagree, but it seems, well, technically we can live without this vertex, but also the other things that we, well, Misha, can we say about DAHA a little bit? What do you think?
I don't know. I have class like in 5 minutes. You can
Or
say whatever.
maybe because it's still some work in progress. So it also allows us, if we actually refrain from this condition that this product is 1, we can actually produce some deformations of this structure. 1 parameter deformations. And this is again, this is now working. Another
So
work
would you say that adding this extra vertex is a kind of shadow of solving your problem in a kind of deformation, where you put your problem into a deformation family and somehow that things become easier?
Yes, exactly right.
Much
And
easier.
it's related to this two-dimensional genus 2 generalization of DAHA by Artamonov and Shapiro.
I see.
Yeah. Well, by the way, Leon, it's one slight comment. Schrader is the first. Schrader spelling is Schrader, not Schrader, and I think that Semyon Artamonov is also included in the list of co-authors of what you.
Okay. That's, the list is growing, right?
Yeah, well, I'm sorry for.
No, that's fine. That's fine.
Okay, thank you. Yeah, that's very cool. Yeah, this relationship with the kind of deformation idea I particularly like. Okay, does anyone else have any last questions? If there are none, then let's thank Leonia once again.
Well, thank you for your attention. So at least I probably have to stop sharing its screen, right?
Right. Yes. So yeah. So there will be
You might
another
stop recording or someone.
Right. That's true.